Let's go ahead and get started. Today we're going to finally go to a different data structure, binary trees. So far we've talked about an array, which is a contiguous piece, and we talked about a linked list, which is a linked data structure because it forms links. A binary tree is going to be similar to a doubly linked list, except for that there's a specific ordering on what's to the left and to the right, or what's previous and next. Instead, it's going to be left and right. And we're going to apply a certain ordering on it, which will help us out. And that's nice slides. That's great. Okay, here's a beautiful definition, but that's not too helpful. That is somewhat helpful. So here's a picture of a binary tree. Okay, there are many different types of binary trees. And then there's different subtypes of those binary trees as well. So first off, there's the generic binary tree. And the generic binary tree means that there's a root node, on this case it's A, and every node has at most 2 children, hence the word binary. And then those children can have up to 2 children as well, so forth and so on, until you get to the end. So you have A is part of a binary tree, or the root in this case. Left is B, and right is C. B has D and E. D has nothing to its left, but to its right it does have one child, which has no children of its own. In a binary tree, it is strictly enforced that you always have at least 2 pointers, because those pointers may point to nothing, or they may point to a null. Nothing or point to another node. All right, let's see if we can do another picture. All right, the slides do want to go through this. Say, hey, look, there is a limit to the number of different instances of a binary tree. If a binary tree has 1 node, there's only one way that can be. All right. If it has 2 nodes, you basically have 2 options. You have the A with B on the left or with C on the right. Now with 3 nodes, you have multiple options. Here's one option here, and then you have some more options. Notice that you can go AB and then D to the left, or AB and a node to the right, or you go AC with a node to the right, or AC with a node to the left. Ooh. All right. That's a lot of options. Okay. All right, now we're going to skip ahead because this I don't think is, well, we'll go ahead, yeah. Oh, we'll talk about this real quick because this is a helpful picture. So when thinking about a binary tree, you have your root pointer. This is like your head pointer of a linked list, except for you have a root pointer. Why do we need to store a pointer? Well, if the tree is empty, then the root pointer points to nothing, so you know that there are no nodes in your binary tree. If there is something, you need to point to the top of it, because since it's a tree, oh, by the way, think of this as a tree going down as opposed to up, or you can think of it as the root system of a tree, whichever way you prefer. Why do we start at the top and go down? I don't know. But that's the way it was chosen. Well, and I can take a guess. My guess is because when you're doing anything computer on a screen, you're always starting at the printing at the top and then you print down. So most of the time we think of things starting at the top and moving down. That's my guess. I don't have the exact historical reason. All right, so you have a root node in case there's nothing. Great. All right, we'll go through all these definitions. I will pretend like you have them memorized, and then I will remind you of each of them because they'll pop up again. A leaf is a node with no children. Which ones are leaves? Or I guess leafs in this situation is the correct term.
G, E, and H.
D, G, E, and H. Correct. Thanks. U is a parent of V if there is a branch from U to V. So what's the parent of E?
B.
And what's the parent of B?
A.
So what's the relation from A to E? Take a guess.
Grand.
There we go. Well, it's the grandparent. Yes. All right, we got it. There is a unique path from the root to every node. Ooh. If you're at A, is there more than one way to G? No. So this is important because you can't go A, B, E, and then have E point to G when you have A, B, D, and D pointing to G. You're not allowed to do that. So there's only one path from the root to node, and that consequently means that there's only one way to get to a node from any node, as long as it's in the tree. By the way, subtree, if you, well, I can't put my hand over that, but if I were to just look at this section right here, is that a binary tree?
Yeah.
With B as the root? Yes. So you can have subtrees, or consider things as subtrees. That'll be very handy when you start coding this up, by the way. The length of a path is the number of branches on the path. So what's the length from A to G?
3.
3. Remember, it's the number of branches or the number of links. And the level of a node is the number of branches on the path from the root to it, and the root is level 0. So what level is E on?
3.
A is 0.
Oh.
2. Right. Yeah, we start at 0. Height of a tree is number of nodes on the longest path, which is probably what you were thinking of. So what's the height of this tree? How many nodes are on the longest path? 4. That's fine, because if there were no nodes, then the height would be 0, because root would be pointing null, so we do still count it from 0. All right, that's great. Now we're going to either go to an example, or I'm going to do it on the board, because this is getting ridiculous. Binary search tree. The whole point of this right now is a binary search tree. We are going to go to a different type of binary tree, but right now, for today and for a little while, we're going to talk about the binary search tree, because that is, in general, the most implemented version of a binary tree. So a binary search tree is the rule is it's a binary tree where everything to the left of you is less than your value, and everything to the right is greater than your value. And hopefully we can see that from the picture. So we have 78, 32. Oops, that's not true. What's that 89 doing there? This is man, they messed this picture up. This is wrong.
Yep.
That is wrong. Let's look at this. That looks correct. All right, now that we're on an actual binary search tree, 60, 50, 30, 58, and 46 are both less than 60. They're all less than 60. 70, 80, and 77 are all greater than 60. Okay, cool. All right. I wanted to get to this so we can start coding this up, because just adding nodes to a binary tree is kind of, when you don't have a scheme behind it, it doesn't make a lot of sense. You're just kind of picking nodes. But now that we have a scheme, namely you want everything to the left be lower than it and everything to the right be greater than it, at least now we have a scheme for creating a binary tree. All right. Oh, any questions? We're going to fill in a lot of details as we code, and we're going to jump back. But you have the general idea? Excellent. So let's go code this up. What's the big F do? Oh, yes, the flying. Excellent. All right. Where are we? Class code. Binary tree. Okay, so let's go into source real quick. Oh yeah, we don't want this. Ooh. What's in test? Oh yeah, we don't want that. Let's go test. Actually, let's move it. Test. Minus test to test, and we'll call it BT test. That's P, because I don't want to type out binary tree. All right. Actually, we don't know what we're including. Let's do class binary tree. Ooh, that's kind of weird. That's much better. All right. So jumping back here, what's a binary tree going to consist of?
A root. And
A root. And what's the type of root? What's
Pointer.
root? It's a what, sir?
Pointer?
It's a pointer to a
Node.
node. I guess we gotta make a node.
Yeah.
We're going to call it this so I don't have to type everything out. All right. Let's make it a binary tree of integers to make our lives easy. So what's the node going to have?
The value up pointing to the left and right.
You got it. Let's do it. All right, hold on. So, what you meant is correct. What you typed was wrong. And let me clarify this because this this trips up a lot of C programmers. What has been declared just now is a binary tree node. Left is a pointer, and right is the actual BT node. To help avoid this problem, write your code like this. So when you're declaring variables, put the star next to the variable. Yeah, because it looked like it was actually declared both of them as pointers, but that's not what's actually happening. That is a little intricacy of the language. I'm not trying to jump on you, whoever typed that. You had the right idea. All right.
No, that was very helpful.
Okay, good. So, all right, I declared them private. We can make them public, or we can do getters and setters. Which way do y'all want to do it?
Public.
Public, all right. Let's go. I'm going to fix that real quick. Well, that made that easy. All right, but let's go ahead and make a constructor. I do like to have the constructor. It makes things at least somewhat easier. Ooh, that was fun. Let's try that again. Let me update my variables. Perfect. All right, let's go make sure this compiles. Oh, good. All right, what does this contain?
Node would help contain a root.
Right, so let's do a root, and what do we say its type was? Again, put the star next to the variable. This is just to prevent you from making that error again. There, perfect. All right, so we have root. Good. All right, I'm going to go and fill out some functions. We want to have a constructor. Oh, that was weird. We want to have a deconstructor. We want to be able to add a value. We want to be able to tell if it contains a value. All right, we want to be able to add it. We want to be able to ask if it contains. A function that we're not going to do today is delete, but I'm going to go ahead and put that in there. I'm going to call it remove. I want to put it in here so you see that it's a very common function, but it is more complicated than what I want to cover in one day. After all, you do have, what, Project 2 due in a week? So.
Get back up on the hard stuff of this.
Well, yeah. Well, we're the beginning of the course. I'm like, can we just get through this part, like the whole build up, so we can start knocking these out. But yeah, I don't. At this point, doing remove, I think, is kind of beyond the scope. So let's focus on add and contains for now. There's another function that I'll let you get to for the lab, but add and contains are very good for today's lecture. All right, so let me also open up BT node. Okay, so this is the maze. So let's binary tree. That's
Did you call it BT something?
I did call it binary tree.hpp. Good catch though. Probably should, but that's fine. Let's see. Test simple. All right, so we're just going to TS assert. So let's. I'm going to keep that TS assert around so I can remember what I need to do. And look at all those tests. I'm sorry, guys. 1 moment. Thank you. All right, so let's do what I call it. I call it a binary tree. Excellent. So binary tree. I'll call it BT. And let's test assert BT dot contains 0 should be false. Right? And if we do BT.add 0, I don't think that one has a return, does it? Nope. I'm going to go ahead and give it a return, just to emphasize that for the binary trees in this class, you can't add the same element, just for this class, for now. And then this should be, of course, true. All right, good. Let's see if we can fail this test case. Class code 13. Ooh, expected unqualified ID before token. Oh, on HPP line 18. Line 18.
Oh, I see.
Oh, yeah. Well, no, a good guess, but I think Elena pointed out. That's actually what it's supposed to be, right? Oh, almost there. Undefined reference to binary. Yeah. Okay. True. All right. So let's source .cpp. All right. One day I'll put in the plugin that automatically populates this for you, but not today.
Mind telling me what it's called so I can do it?
I forgot. There is one. I'll just return false, and return false. All right, let's see if we can fail some test cases. Nope. Expected before token. Did I forget to include? No, binary tree.hpp. Oh. C++. Oops. Let's try that again. Good, we failed. All right. That's right, I'm happy when we fail. All right, so what are we trying to do? We create a binary tree, we ask if it contains 0. Looks like we pass on that. And then we try to add 0 and we return false, probably because we don't do anything in our add function. All right. So, step 1 when doing good test cases, we wrote a very simple test case. Let's just make that one test case pass. What can we do to make that one pass? What do we want to add? What's the first thing we need to do?
0.
What? Sorry.
We need to add like the first value to be 0.
Okay. Yes. Oh. Let's jump back a bit. Here it doesn't show a picture, but we have root pointing to nothing, and then we want to have a node. This one's labeled A, but we want root to point to basically 0 with no children. How can we do that?
You gotta make a node.
All right, let's do it. It was val. It had 3 parameters. The first one was the value. So this would be val. And then its left and right children. Oh, we're using C++. Okay. All right. Now what do we do?
Could just
Oh,
set head to or whatever.
Yeah, let's just do that.
No.
Thank you.
I was hoping that would slide. Oh, at least let me do this. There.
I deal with this a lot.
Whew. All right. Just FYI, when you do go to a team, they will probably have coding convention standards. There are, from my experience, the good ones, effectively, the best ones, in my opinion, are the ones that you stick with the coding standards of the file. That's my best ones. I think are the best. They do put some like, all right, you need to tab and do other things, but usually stick with the file. But yeah, we all have different ways of doing it. There's some really ones that really drive me nuts, but this is a minor one. Anyways, are we returning false? Let's return true. All right, let me save. Let's see, so we failed on line 17. Now we failed on line 18, great. And that, I believe, is the contains function?
Yeah.
Yep, good. All right, so yeah, how are we gonna fix contains? All right. I like that. Let's give it a try. Ooh, seg fault. Let's, did I put in -G? Great. So let's Valgrind the test runner. Unless one of y'all sees it. Does anyone see it? Nope. Okay, that's fine. Okay, hang on, let's jump up here and see what's going on. All right, use of uninitialized value of size 8 on contains on line 17. So we're at line 17. Ooh, uninitialized value. Well, there's only one pointer you're dereferencing, and that's root. Huh. Well, that's interesting. When is it that's happening? That's happening on line 16 here. So, what that means, well, that was weird. Okay. What that means is line 16, aka when you do your first contains on 0, Valgrind is telling you root is not a valid value. How do we fix that? Right, yep. Okay. Help him out. Sorry, it happens to me too.
I can't type on this thing.
Perfect. Oh, almost. There we go. All right, let's save that. Let's see if that fixes the problem. Whoops, I need to compile it first. Null is not declared in the scope. All right, there's different ways to solve this. We'll just do that for now.
That must be why it's always at the top of the labs.
Oh, include standard lib?
Yeah.
Yeah.
.h.
Yeah, it has the null pointer, as he was pointing out, is it's pointed to the C++ standard. I'm too used to just typing null in all caps. All right, let's do the Valgrind again. And, oh, conditional jump or move depends on so it's interesting that seg faulted when I ran it, but under Valgrind, it actually ran and passed. Okay. Do listen to Valgrind. Valgrind is very good at sometimes doctoring up your mistakes and fixing them so your program can still run, but it's still going to tell you if there's a problem. And it says right here, conditional jump or move depends on uninitialized values. That means that there's that means a lot of things. All right, on line 18 from simple, so it's still the same one. Okay, if root equals null, so it's saying that on this line, you are dependent on an uninitialized value. What is uninitialized? Hold on, that line of code is correct, or is a correct way to do it. But what variable could possibly be uninitialized on there?
Root val?
Root. Why is it uninitialized?
Is it because it's not initialized in the HTTP file?
Or it wasn't initialized in the constructor? Here, one moment. Oh, okay, that works too. Go ahead. You got this. Perfect. What was happening is Valgrind was very nice, and when it recognized that you were using an uninitialized value, it probably threw in null in there for you. But a real program is not going to do that. So that's why we seg faulted here, excuse me, but Valgrind was able to catch it and move on. Now I bet you if we make it, there, we just pass. Okay, well good, there was some nice debugging going on there. All right, so we got null there. Okay. We're going to do test. We're going to do test multiple now. Let's go ahead and take this guy, copy it down here. All right, let's see if that passes. Oh, my Windows Manager's having problems. It passes? Oh, it does. Yep, that's funny. Let me rearrange this then. I don't know why it passes. All right, let's add 0 through 3 and then see if they're in there. They should all be in there. Nope. 29.
You set the root just to the...
Yeah, when you set the root conveniently, yeah. All right. So that is a failure. I'm going to pause the video for now because we're going to get into some a little more complicated coding.